Alright guys, so in this video, continuing on our vector talk, we're going to start looking into a lot of definitions. I will say this video is high in definitions today, and a little bit of examples to go along with it, but mainly kind of just to really show some definitions and define some properties used in vectors. So as you can see, our goal for the video can be seen above. So let's dive right on in and find out what the game plan is for vector addition and scalar multiplication. So we talked about the differences between scalars and vectors. All right, let's kind of scroll back up here for a sec, just for a quick little reminder that we talked about, right? So our vectors have direction and size, where scalars just have size. And so we can think of our vectors as a way to think about displacement and velocity, and scalars is more so on the concept of distance and speed and things of the nature. And we'll get to that in a little bit deeper lesson in a little bit later video. And so for now, let's just see about, we've already talked about component form of vectors. Now, what happens when we add actual vectors to one another? Now, we're going to look at some definitions here, and in the next slide, we're looking into some visuals as well too. So as you can see, we are looking at letting u equal u1 comma u2, the vector u1 comma u2, v being v1 comma vt. If we are adding or finding the sum, or also you might hear it as the resultant of the vectors u and v, you will add our two x components together, or u1 and v1 in this case, and add our two y components, or u2 and v2 in this case. Now together they will make one component. Now for scalar multiplication, scalar, remember, is just that constant. Scalar is just a value. And so when we are multiplying a scalar to a vector, it's almost like the distributive property. You'll just distribute the scalar to the x-coordinate and the y-coordinate of the component form. And the last one that you're going to see on here is our opposite of a vector. Okay, so the opposite of a vector is obviously the negation of it. It's that negative v. But we can also think of it as being multiplied by the scalar of negative 1. So another way to kind of think about scalar subtraction in a sense, or excuse me, a vector subtraction in a sense, is by saying, hey, u minus v, well, it's really the same thing as just saying u plus negative vector v. All right? And again, that's not reinventing the wheel or anything. That's basic algebra that go along with it. You can see that the vector subtraction is just the addition of the negation of v, or whichever one was second, of course. All right. So that's kind of some of our basic definitions, and if you need, of course, pause the video. You can pause the video at any time to get these down. But let's take a look here at how can we maybe visualize this a little bit more so. Well, before we visualize, I also want to talk about a vector that we use later on in our lesson as we start talking specifically about velocities and speed and things of the nature. But let's talk about the unit vector here for a sec. You might also see a vector, all right? So let's go ahead and say that we have the vector v over the magnitude of vector v, all right? This particular vector has a magnitude of 1, all right? All right, it's the magnitude of 1. And so we call this the unit vector, okay? So this is a magnitude of 1. It's the vector divided by itself, right? So it's the unit vector itself. Now, in terms of component form, we could also see this as cosine of the angle, whatever directional angle we're talking about, and sine of the direction angle. Once again, now, theta is the angle of direction for the vector v. All right. Also, we may see the same thing called the direction vector as well. All right, so it could be the unit vector, it could be the direction vector, because really it simply tells us what is our direction of motion. How many units along x, how many units along y, that's what we're going to really be seeing there. So we kind of see it all as a couple different definitions. All right, so moving on. Now let's talk about, we've already talked about tail to head representation. All right, we've already kind of seen the head minus tail kind of thought process here. And so, but I want to visualize, I want to show a visual representation of what tail to head looks like. So tail to head representation. And then on the right-hand side over here, we're going to look at parallelogram representation. Parallelogram representation. All right. So first and foremost, let's take a look at tail to head. So let's say I've got my axes, and we'll go ahead and deal with red. And so, no, we'll do blue to start off with. We'll do blue for the two of them. So let's say I've got a directional vector u, and then I have another vector v, right? So together, all right, this is our vector u and our vector v, all right? But there's an addition happening here, right? I'm basically saying, all right, well, what if I added u and v together? What if I added the vectors u and v together? Well, to represent this in terms of a tail to head representation, we could sit there and connect the tail of u to the head of v, and this would be considered u plus v. Remember, we put little lines underneath just to kind of represent vector in this case. But there would be our u plus our v. All right, and then kind of think about what's happening here, right? This is kind of that u1, u2. That's what our point is focusing. The arrow from the origin to u1. So here's going to be u1, u2. So u1, comma, u2. And then we kind of go from u1 to our v1, v2. Well, to go to our end result here, I would take my u1 plus v1 and my u2 plus v2. All right, so to go from, I'm following the line right here, so to go from u1, u2 to the head of v, I would take whatever u1 is plus u2, all right, and u2 plus v1 and v2. So that's kind of our standard representation of u plus v. But you also might see it in parallelogram representation as well. So let's say, once again, we have our axes here, and we'll keep it consistent. We'll keep blue going on, and let's say I have u right here, so my vector u, and then we'll say maybe down here we have our vector v in this case. And now we also might see a parallelogram representation in this example. So now how do we get a parallelogram representation here? Well, the sum of u plus v in this case, well, they both start at the origin. And so the parallelogram representation has to start at the origin as well too. And so we got, in this case, more like a vector of u plus v in this example. Where does this whole parallelogram concept comes on into play? Well, take a look. Connecting here and connecting here, you kind of see our parallelogram representation happening. And so that's where we get our parallelogram representation from there. All right, so two ways to represent vectors: addition, almost geometrically, tail to head, and parallelogram. All righty. So now let's kind of dive into, before we go into one example, let's talk about some properties of vectors. So some properties of vectors here. So as you can see on the screen, we have some properties dealing with the vectors, letting u, v, w all be vectors. A and b are scalars. You can kind of go through, I'm not going to read through every single one of those, but you can kind of see what happens here through all the properties. I'm hoping to start to realize that this is very similar to just basic algebraic properties. It really, really is. There's not too much of a difference between them. I mean, take a look. 0 times our vector equals 0. 1 times the vector equals the vector. You know, this is extremely similar to what we see in our basic algebraic properties as well too. So make sure you have these vector properties of operations down. And we're going to take a look at a couple examples here. So our example we're going to deal with, I'm going to say, hey, let the vector u equal the component form of -1, 3, and let the vector v equal the component form of 4, 7. I want to go ahead and find the following. So part A, my goal is to find the scalar 2 times vector u plus 3 times vector v. All right. So in doing so, I like to go ahead and just kind of do that scalar multiplication first, and then we'll kind of take care of the actual addition thing. So this is looking like 2 times the component form of -1, 3 plus 3 times vector v's component form of 4, 7. So this becomes -2, +6 plus 12, 21. And now we can take the sum. So you want to add your x's together, your x coordinates. I kind of say coordinates, not really coordinates, your x direction, all right, and your y directions on together. All right, so let's take a look. We end up doing so. We end up getting -2 plus 12 and 6 plus 21. And so -2 plus 12 is going to be +10 and 27. And so there would be our vector form, or excuse me, our component form of the vector 2u plus 3v. Let's take a look at another example, say part B. So for part B, I want to go ahead and find u minus v. u minus v. Well, again, we're just kind of matching up the x's to the y's. So we have -1, 3 in our component form, 4, 7 in its v's component form. And so we have -1 minus 4, 3 minus 7. In the end, -1 minus 4 is -5, and 3 minus 7 is a -4. And so we should see our component form at -4, -5, -4. So -5 in the x direction, -4 in the y direction. And then lastly, what about taking the absolute value of 1/2 u? All right, so 1/2 u. I'm going to go ahead and erase our previous one here. I'm going to go ahead and erase this real quick. Make a little bit of room. In part C, we are going to go ahead and try to find the absolute value. So part C, absolute value of 1/2 of the vector u, 1/2 of the vector u. So what are we looking at here? Well, remember absolute value? Absolute value really recognizes in vectors not absolute value, but really magnitude, right? It's the size, it's the length of the actual vector. So we are really finding, when you see these kind of absolute value looking bars, you're really looking for the magnitude of the vector. So it wants the magnitude of half of vector u. All right, well, let's first and foremost, just like PEMDAS, go inside out. So inside of vectors of -1/2 is just -1/2, and then 1/2 of 3 is just 3/2 in there. And so we're looking at the magnitude in this case of -1/2 minus 0 squared plus 3/2 minus 0 squared. And again, guys, we utilize this 0 because you have to kind of assume that it's starting from the origin. That's all we've got going for us. And so simplifying this on out, we end up seeing that we get square root of 10/2. All right, so 1/4 plus 9/4 end up giving yourself square root of 10/2. All right, ladies and gentlemen, that's going to wrap it on up for this lesson here. As we kind of go through, I got one I want to give you a shot on your own. So let me kind of scoot down to our last page here. And let's take a look here. What if I said u equals, the vector u is 3, -2, v is -2, 5. And once again, I want to find, part A is going to be find the component form. Find the component form. And then part B is going to be find the magnitude. All right, find the magnitude. So your first example is here. Give this one a shot. Let's say you are looking at -2u plus 5v. All right, -2u plus 5v. And I want to find the component form and find the magnitude. Hopefully for part A, you come up with -1629. And for part B, you get root of 1097. All right, folks, and we're on to the next one.